5.3. Okay, so we just finished up 5.1 and 5.2. We looked at just briefly at this system in Scotland, and now what we're going to do is hop into 5.3, and there's the what's mentioned here is the world resource. So if you kind of remember, like chapter 1 or chapter 2, we talked about how primary energy hits the planet from sun and where all of it's flowing. We talked about how much energy flows through the hydro system, if you will. And so the world resource, so in fact it mentions figure 1.9 that almost a quarter of the 5.4, so let's write these numbers down. So again, we're looking at world resource. So 5.4 million exajoules. It's kind of a weird way to write it, but there we go. 1.5 billion terawatt hours reaches the Earth's atmosphere every year, is turned into water. So one quarter of that. So 1.4. So we're talking. Let's just do the math really quick. So 5.4 divided by 4 equals. So we basically got 100. Let's see. So 1.35 million exajoules. Let's write that down. So 1.35 million exajoules. Now, how many exajoules does humanity consume per year? 500. So again, let's write that out and see how the math works out. So and I think what we'll notice is that there's no real energy shortage in a lot of ways. We talk about that, but I think it's just how we apportion our technologies. So 1.5 million. So E total equals 1.5. 1.5. Now let's think about how to do this. E6 times 1E18. So I just took 1.5 million times 1 exa.
Okay.
So there's a big number, and so that's the E total, and this is in joules. Yeah, and now let's look at E used in joules, and this equals 500 E18. So that's how much we use. Enter. Make this a little bit bigger. So this is the amount of energy in joules that passes through the evaporation cycle. This is how much we use. So let's look at our capacity factor, if you will. So the CF equals this number divided by this number. That's tiny. So and we can also do it as a percentage. Equals that. Control 1 percentage. So this is saying that if we as a civilization were able to capture all of the flow of water up and down as a result of evaporation, got more than enough. So if we take the inverse of that, equals 1 over that number, there's 3,000 times more energy resource in hydro than we're using. So no shortage there. It's kind of impressive that it's that much. And you can do similar things for geothermal. You can do similar things for tidal. So it's really up to us now as a civilization to realize, hey, there's plenty of energy out there. We don't have to keep burning through these fossil fuels. Okay. But now, so but the total resource that's given at the bottom. And so we can turn this into let's take this and turn this into E used, and we'll put this in. Let's do megajoules first. Equals that number divided by 1E6. Now let's do E used in kilowatt hours. What's the conversion between megajoules and kilowatt hours? 3.6 kilowatt.
3.6 megajoules per kilowatt hour.
3.6 megajoules per kilowatt hour. So equals that divided by or multiplied by 3.6. I'm having trouble thinking on the fly right now.
Wouldn't it be multiplied?
1 kilowatt hour is 3 point mega, so we got to have a smaller number, right?
We would divide.
Did I do that right? Let's just double check. I always get this messed up. So a kilowatt hour to megajoules. 1 kilowatt hour is 3 megajoules.
2.6 megajoules.
Sometimes I have trouble thinking in reverse.
Or you can do 1 megajoule equals 0.278.
Yeah, so this number's smaller. I think I got that right. Yeah, Levi's nodding his head. Thanks. Okay. Control 1. We'll put that in scientific. Perfect. Okay, so that's kilowatt hours. Now insert. Let's convert kilowatt hours to terawatt hours. So to get from kilo to tera, we got to go through mega. We got to go through giga, and then we got to get to tera. So 10 to the 9th equals that divided by 1E9. Okay, so 1.5, and then we'll insert it one more time, and we'll take this guy. So this is terawatt hours. And now let's take this thing and say equals that, dink, and we'll change it into that special format. Control 1, special, no, custom. We'll go engineering units with it. Where'd you go? There you go. Okay. So 140,000 terawatt hours. Okay. Now I think we're prepared to look at table 5.3, because we can see that the total resource is, insert, I'm going to say energy resource. This is in terawatt hours, and this is table 5.3. What's he say there? 39.8 terawatt resource hours per year. So let's see here. Resource, technical potential, percentage of technical potential. Okay, So the numbers we're seeing in terms of technical potential are 15%, 18%, 17%, et cetera, et cetera. You can see the Middle East is a very low percentage in technical percent because they just don't have the topography. They don't have the lakes and the rivers and what have you. Asia, quite high. Big mountains. The Himalayas, et cetera, 35%. Oceania also very small because of its low elevation. Now the technical potential is 16,000 terawatt hours per year. The total resource is 39,000. So we're kind of we're in the ballpark. I mean, you're sort of looking at 40,000 terawatt hours per year, and the whole planet consumes 140. So hydro, if implemented, could provide a big fraction. I mean, we sort of eclipsed. Our energy demands have eclipsed what hydro can provide. But anyway, yeah. And what it says here, the 40,000 terawatt hours per year is what this flowing water. The water is just sort of flowing what's there as a resource. The technical potential is what you can actually go out and build on a economic basis. Okay, so we're in the ballpark. Those are big numbers to be throwing around, but I think we've got a handle on it now. All right, now national resources, the next one. This is table 5.4. China has the largest technical potential. Russia is second largest. USA is there as well, followed by Brazil. You can see that Brazil and also Norway, Norway, 96% of the country's electricity provided by hydroelectric. Pretty impressive. Venezuela also quite high at 69%. Sweden 49. Switzerland 52. Brazil is at 84. The U.S. is only at 7. Because that's just because we use so much dang electricity. A lot of that's coal, a lot of that's wind, but as we know, that's changing quickly. Okay, average capacity factor, the highest is Venezuela, and the lowest that I'm seeing there is Italy in terms of how much it's using based on what it actually has. Okay. Now, if we look at the next little figure, we can see how the world output, and so now we're looking at terawatt hours per year. So 3,000 terawatt hours per year. How does that compare to what we were seeing previously? Remember, the technical potential is 16,000. The current world output is just around 35. So this means that if we just keep going forward with producing hydro, we can quadruple what's available. Assuming the environmental factors actually pan out. So this curve does not really show any kind of sign of peaking, if you will, in the same way that uranium did when we saw uranium resources in 101. The same way that coal and gas, or not, I guess coal is sort of yet to peak, but the same way that oil has essentially peaked. So there's a lot more potential here. And this doesn't include the pump storage. Remember, this just includes the primary resource. Okay, so that's climbing. Okay, so that's kind of the big picture. Moving on to 5.4, this is small-scale hydro. So in box 5.2, what they're trying to do is define what small-scale hydro is. We built a very small-scale hydro this summer out in the Clark Fork. We built a kind of a Mark Twain-style electrical generation system. But let's just read box 5.2 and see what it says. General view of most international energy organizations is that a plant should be recognized as small scale if its capacity does not exceed 10 megawatts. That's actually pretty big. I mean, we ran the numbers on the Clark Fork River a few years ago and decided with just a few feet of head and the flows that we're getting, 2,500 to 25,000 cubic feet per second, we could do about 2 megawatts just with the Clark Fork. Kind of just here in the dam. And I don't know. There was the Milltown Dam back in the day. It was taken out. I don't know what its output was, but it would be considered small-scale hydro. It's not going to be as big as 10 megawatts. It says, unfortunately, this definition is not universally accepted. Whilst a number of countries, Switzerland for interest, use the above figure, many prefer their own criteria. A notable example is India at 25 megawatts. The U.S. is at 30. So it's just a relative measure of what small is. And China says 50. So couldn't include a plant powering a small city, etc. So in publishing national energy data, the UK includes as renewables all hydro output regardless of the plant size. That goes without saying. However, as in many other countries, a much more detailed breakdown is used for different levels of government support. The term microhydro is commonly used for plants with capacities below 100 kilowatts, and picohydro for very small plants, but there's not an agreement. Our system in the Clark Fork would be called picohydro. All right. Okay. Okay, and then finally there, box 5.3, the Elan Valley in the Cambrian Mountains in mid-Wales. This is 5.6. That's what we're viewing right now on the screen. It shows some of their smaller capacities. So the Craig, the Pennygarrig, the Caban, the Fowl, these are all in the order of, below 1 megawatt, so 480, 810, 950, 300, and different turbine types. Okay. Yeah. Oh, one thing that's mentioned here, and this is kind of important from an environmental standpoint, it says large-scale hydro may be renewable, but is not a sustainable source since its environmental and social consequences are such that it fails to fulfill the essential requirements for sustainability outlined in Chapter 1. It says, but small-scale plants are inherently free of the main deleterious consequences that accompany, like getting rid of an entire ecosystem is considered, non-sustainable. Okay. The debate seems likely to continue, is sort of how 5.4 wraps up. Okay. Oh, another thing that is worth mentioning here, this chapter is on hydroelectricity. So you're taking one form of energy, notably gravitation and mechanical, and converting it into another, electrical. But what's mentioned here is water mills. So a water mill is something that's just going from one mechanical form into another. And typically you think of mills as a grinding or type of deal. And the same confusion is sometimes between wind turbines and windmills. Some people mistakenly call wind turbines windmills, but if it's making electricity, it's a wind turbine. If it's pumping water or grinding corn, it's a windmill. Okay. What's next? Well, let's go ahead and move on to 5.5. Here's an example of a pump storage facility. And I think I'll just keep going for another 15 minutes. We'll just get as far as we can in the chapter. Okay. So potential energy, as we know, is energy equals mgh. That's old hat from 101. The equation that's given is stored energy, E stored equals 1,000 times the volume times the gravity times the height. Where's this 1,000 coming from? Well, that's just the density of water. So we know that mass, m equals rho v. So we know that the density of water, so rho H2O equals 1,000 kilograms per cubic meter. So obviously the mass here is measured in kilograms, the volume is measured in cubic meters, so this 1,000 is simply the density of water. That's where that 1,000 comes from in equation 1. And this might be the first time in the book where the equation is actually numbered. So think about that a little bit, when you're writing your NRGY 102 summaries, and I don't know why they just decide, oh, it's time to number an equation, but there it is. Yeah, it could be that later in the chapter they reference it. Okay, and then these are all obviously in SI units. Okay, so there's pump storage. We talked a little. You could think of this in terms of what's going on in Gordon Butte. We talked about the discrepancy between 400 megawatts versus 800. The Gordon Butte turbines, both the pump and the turbine spin in the same direction, and so you could have actually, well, what would it be? It would be a flow in this direction, from the top to the consumer, but at the same time you would be pumping up in a separate shaft in here, taking water from the reservoir. So it's essentially idling. It's so weird to think about. So making and consuming 400, so that adds up to 800, but in total it's 0. It's not doing anything. But that's just the way it's designed, so it doesn't have to switch and actually change its direction constantly, as was depicted in that figure. All right. So here's the Kuchan pump storage plant. The installation is shown at the top, and I don't know if this guy is actually in exist. That's not ideal. I think it'd be. Let's just see if this guy's been built or not. A lot of these things are just kind of coming online as this is being built. It looks to me like the figure 5.8b is a drawing. Pumped storage. Let's just take a look here. That looks real to me. It is located. There it is. 400 meters, location, 4 generators, 400, so it's it's on par with what's going in at Gordon Butte, fairly substantial. Okay, so that's this guy in Scotland. Next, they're looking at power. So let's dig into those equations a little bit. So we've looked at energy. Now let's look at power. And oh, by the way, this symbol that I just used here is rho. It's not a p. It's a rho. And if you write this thing down, what you'll want to do is just make it like this, as a single stroke. Whereas if you're making a p, they'll do it like that. So you get that little tail on there. So that's the difference between the P for pressure, or obviously big P for power. So this is power, that's pressure, and that's density. Sorry, but that's just the way it is. So big P for power, little p for pressure, and then that row looking thing. And if you're looking to use that in one of your equations in Microsoft Word, the way I found it easiest to do, let's let this guy start up here. Come on. Well, maybe I can do it in Excel. It's the same thing. But if you put the letter R in there, highlight it, go up and turn that into symbol, there's your row. So just the Greek equivalent of the letter R. Doesn't look a whole lot like it. It's just kind of like an R that the top ended up looping all the way back, I guess. So it's just the evolution of handwriting over time. Yeah. Yeah. Okay. So we talked about energy. Now let's dig into power a little bit. So I mentioned this briefly before, but now we've got big P for power equals 1,000, and that's again your kilograms per meter cubed. I'm going to go ahead and put the units in, and hopefully they'll work out. Times Q, and that is, I'm just going to say Q. They've got this cubic meters per second, so meters cubed per second. So I'm just adding the units in, they're not in the book. Times G, and this is meters per second squared, times H meters. And so that's kind of nice. That's just how high the dam is. Okay. Now, if we write the whole thing out, let's just forget about the well, no, we won't forget about it. Let's just write it out like this: 1,000 Q G H, and now we've got kilograms, meters cubed, meters. So I'm just writing out all of the numerator units together, and in the bottom I've got meters cubed, seconds squared. So I'll just keep on going. 1,000 Q G H. Let's cancel some units. Meters cubed cancel. These become meters squared. Now we've got kilograms, meters squared over seconds cubed. And if you remember back to 101, we've got mass times length squared over time cubed, and boom, we've got our proper dimensions of power. So, it's just double checking. Okay, so the authors then throw in a they get all the way up to equation 4. I'm liking it. I think this was equation 2. Equation 3 has us as power equals 1,000. Now here comes another Greek symbol. This is the symbol eta, and we've seen that in the Carnot chapter from 101. Times Q times G times H, and this is going to be the power 10 kilowatts. They don't have dimensions on that, but if we want to go ahead and turn that into kilowatts, so power in kilowatts, what we're looking at is 10 times eta times Q times H. Now let's go in and see if this thing works out. So Q is measured in meters per second squared, or sorry, cubic meters per second. I'm going to figure out what dimensions are missing from that 10. So this is going to be in cubic meters per second. This is going to be in meters. Eta is dimensionless. So what we're missing here, this 10 combines kilograms. It's also going to have there's gravity's thrown in there too. So you can see that gravity's sort of missing there. Anyway, at the end of the day, you're going to have to have a meters squared in the basement, and you're going to have a seconds squared accompanying that 10 to get your actual power in kilowatts. So if you want to dig down into equation 4 and figure out exactly where those are coming from, you can do a very similar dimensional analysis to what I just did with 2. Okay, so what's mentioned here is that they're looking at about 83% efficiencies in some of these guys, and that's just because of well, there's heat, there's friction, there's also in any electromechanical system, and we haven't really delved that deeply into Maxwell's equations and how magnets work and all that, but magnetic fields themselves are leaky. It might sound a little bit weird, but if you dig down into some of the technology, and I think that's well, it comes a little bit later in the chapter, but something to think about. Every one of these systems that is making taking mechanical energy and turning it into electrical energy, there are spinning magnets inside the technologies. The spinning magnets, and we touch a little bit on this in electricity in our electricity chapter in 101. These fields, they look like this. They're giant toruses. Kind of looks like somebody with really large ears. But the strange thing, the beautiful thing, the curious thing about magnets, these fields kind of like stretch off to infinity. If you keep the analogy going of what a magnetic field looks like, it's this big toroidal deal, and as it turns out, you're never really going to be able to confine all of those fields. You can sort of put the steel cage around them or all that, like you would in a transformer. But this also lends to inefficiencies, and some of that EM field way out here just sort of goes away. It's just sort of lost and absorbed elsewhere. So that's also a source of where this let's get back in here. A source of why eta is well, it's going to be greater than 0, but it's always going to be less than 1. And just to follow up here, the way to make an eta in Microsoft Word or Microsoft Access is to take an H and turn that into a symbol. So.
Your eta is different than Excel's.
Yeah. How are you seeing that? Oh, mine is different. Yeah, that's because I was a little sloppy. Let me try it one more time.
It took a while.
What I was trying to do is this.
Ah.
I was trying to do that, and I think that little this little part opened up. And more with a U. So that's the.
It's backward micro.
That's the pretty eta. Yeah, I don't know why my etas end up looking like a micro. I need to draw them slower. Yeah. And come back up. Ta-da.
In cursive.
Cursive, yeah, so pretty. Okay, well, let's stop there. We'll pick up and look at some of the technologies on Thursday. It's funny, this figure 526. I'm reading that there's that New York Times bestseller, Boys in the Boat. I don't know if you heard of it or not, but it's a talk of how the Seattle men's rowing team ended up winning the 1936 Olympics, like in the Nazi Germany stadium. It's quite the story. But some of the rowers from that boat worked on the Grand Coulee Dam to make money that summer, just as ways for physical training, and to just pay the bills so they can stay in college and keep rowing. It's quite the story.
During construction of the dam?
Yes,
Yeah.
yes, they're hanging out there, on the whatchamacallit, the belaying wires with 75 jackhammers just going for it. So seeing that picture 526 and knowing that the same guys that beat the Nazis in 1936 in Germany built that sucker is pretty impressive.
That is impressive.
What's that book called?
It's called The Boys in the Boat. It's one of those things, like, everyone's like, oh, you gotta read it. I'm like, nah, I'm done with rowing. I don't care about it anymore. But now I'm reading it and it's hooked. But I think it was the number one,
No one really likes it well,
well,
and you're never cold.
it was good training for a little weatherization on my own.
It's definitely adapted those.
Yeah. No,
Put your thermal energy at equilibrium for a while. No wonder you ride in the wintertime. Here we are at room temperature.
Shauna, you crack me up. Yeah.
You're
All
down
right.
there at water temperature.
Hey, we'll see you Thursday. Thanks.
Definitely,
Thanks, team.
thank you.
Yeah. Okay.
I had to bug you one more time.
Oh yeah.
Brad.
Oh, for sure.
Yeah, I got your signature, but for some reason the registrar's office asked me to ask you
To
to
just-
find Steve.
Oh, okay.
Sure.
Yeah. Okay.
I don't know why.